the scenario presented, the rated input power of the variable frequency drive, or VFD, is used to size the feeder according to Article 430 of the National Electrical Code, or NEC. The fundamental reasoning is that the VFD serves as the power conversion equipment, while the motor functions as the load. The VFD sources current from the feeder to facilitate the conversion of incoming alternating current, or AC, power into the variable frequency and voltage demanded by the motor. Notably, the current draw exhibited by the VFD often surpasses that of the motor, particularly at diminished speeds. Consequently, it becomes imperative to proportion the feeder in accordance with the VFD rated input power. This ensures the feeder's capacity to effectively manage the VFD peak current draw. Consider the illustration featuring 10 VFD, each catering to a 1 horsepower motor, where the rated input power for each VFD stands at 9 amps. As such, the cumulative rated input power for the ensemble of 10 VFD amounts to 90 amps. Building upon this foundation, the feeder should be sized to accommodate a minimum of 112.5 amps, which is 125% of the 90 amp figure. Pertaining to overcurrent protection, adherence to the Busman ASBD motor circuit protection tables is advised to pinpoint the appropriate fuse selection for the amalgamation of motor and VFD. The selected fuse should adequately safeguard both the motor and the VFD. In the described instance, the recommended choice is a 3.210 LPJ SP fuse, acknowledged as the optimal branch circuit protection measure for a 1 horsepower motor. This fuse also extends sufficient protection to the VFD given its capacity to manage currents of up to 10 amps. Exploring the details of feeder sizing for multiple motors or motors and other loads, NEC Section 430.24 dictates the methodology. This section stipulates the utilization of 125% of the full load current rating of the highest rated motor combined with the sum of the full load current ratings of all other motors within the group. It cross-references Section 430.6a. Neither 430.24 nor 430.6 directly addresses power conversion devices or adjustable frequency drives, although these are touched upon in Section 430.6c. Now, addressing the concern regarding the standardization on 5 horsepower VFD for motors ranging from 1 horsepower to 5 horsepower, the rated input amperage at 480 volts for such a drive is 9 amps. Considering a scenario involving a panel housing 10 VFD, each serving a 1 horsepower motor, the feeder sizing calculation diverges significantly based on whether the motor's full load amps or the VFD rated input power is considered. Employing the full load amps of the motors necessitates sizing the feeder for approximately 19 amps, calculated as 1.25 multiplied by 1.8, then multiplied by 10. Conversely, accounting for the input power to the conversion equipment mandates sizing the feeder for approximately 92 amps, derived from 1.25 multiplied by 9, then multiplied by 10. The interpretation leans towards sizing the feeder wiring in accordance with Section 430.24, which, in its determination of feeder wiring, omits explicit reference to power conversion devices. This suggests that the rated input power of the VFD need not be factored into feeder sizing, although it remains pertinent for branch circuit sizing. However, there may be the alternative perspective advocating for feeder sizing based on the rated input power to the VFD, potentially leading to the installation of substantially larger equipment. In scenarios where existing motors utilizing contactors are retrofitted with VFD, adhering to the latter approach could necessitate repulling the feeder to the panels, replacing the main disconnect on the panel, and upgrading the feed to the panel within the Motor Control Center, or MCC, irrespective of whether the actual load at the equipment has undergone alteration. Transitioning to the domain of overcurrent protection, the practice involves sizing overcurrent protection for the motor and VFD based on the motor's full load amps and adhering to Table 430.52. This approach has proven effective over time. Section 430.525 acknowledges the potential to employ alternative fuses for power electronic devices. Specific manufacturers may advocate for quicker fuses to safeguard the electronics, as opposed to dual-element time delay fuses. Consulting the Busman SPD motor circuit protection tables may reveal the optimal branch circuit protection for a 1 horsepower motor to be a 3.210 LPJ SB fuse. However, this fuse selection might not accommodate the full 9 amps associated with the rated input power of the VFD. Addressing the central question, the determination of feeder sizing hinges on whether to utilize the full load amps of the motor or the rated input power of the VFD. The prevailing guidance dictates employing the rated input power of the VFD for feeder sizing. The underlying rationale stems from the VFD role as the power conversion equipment, with the motor constituting the load. The VFD draws current from the feeder to execute the conversion of incoming AC power into the variable frequency and voltage demanded by the motor. Typically, the current draw of the VFD surpasses that of the motor, particularly at lower speeds. Consequently, it is imperative to dimension the feeder in accordance with the VFD rated input power. This ensures the feeder's capability to adeptly manage the VFD maximum current draw. Consider a hypothetical installation comprising 10 VFD, each driving a 1 horsepower motor, where each VFD exhibits a rated input power of 9 amps. The aggregate rated input power for all 10 VFD amounts to 90 amps. Therefore, the feeder must be sized to manage at least 112.5 amps, which constitutes 125% of the 90 amps threshold. As for overcurrent protection, the Busman SPD motor circuit protection table should be consulted to identify the fitting fuse for the amalgamation of motor and VFD. The fuse should be selected to protect both the motor and the VFD comprehensively. In the specified instance, opting for a 3.210 LPJ SB fuse is advisable, as it serves as the quintessential branch circuit protection measure for a 1 horsepower motor. Moreover, this fuse furnishes adequate protection for the VFD, given its capability to manage currents reaching up to 10 amps. To summarize, the appropriate method for sizing feeders connected to variable frequency drives, particularly when multiple drives are involved, necessitates considering the rated input power of the VFD rather than solely relying on the full load amps, of the motors they control. This approach is anchored in the NEC Article 430, which addresses motor circuits and controllers. The rationale behind prioritizing the VFD input power stems from its function as the power conversion equipment within the system. The VFD converts the incoming AC power to the specific voltage and frequency required by the motor to operate at varying speeds. This conversion process entails the VFD drawing current from the feeder, and this current draw can be significantly higher than the motor's FLA, especially at low motor speeds or during acceleration. Neglecting to account for the VFD input power could result in an undersized feeder, potentially leading to overheating, voltage drops, and even equipment failure. When sizing the feeder, the NEC stipulates that you must account for 125% of the full load current rating of the largest motor in the group, plus the sum of the full load current ratings of all other motors. In the context of VFD, this translates to using 125% of the rated input current of the largest VFD, plus the sum of the rated input currents of all other VFD. This calculation ensures that the feeder has sufficient capacity to handle the total current demand of all the VFD simultaneously, with a safety margin incorporated. Regarding overcurrent protection, it's essential to protect both the motor and the VFD from excessive current. While the Busman SPD motor circuit protection tables offer guidance on selecting the appropriate fuses for motor circuits, it's crucial to verify that the selected fuse also provides adequate protection for the VFD. Some manufacturers may recommend specific types of fuses, such as faster-acting fuses, to protect the VFD-sensitive electronic components. The chosen fuse should have an ampacity rating that is sufficient to carry the normal operating current of the VFD motor, but will also trip quickly enough to prevent damage in the event of a fault or overload. In the example provided, where a 3.210 LPJ SB fuse is recommended for a 1 horsepower motor, it's important to confirm that this fuse is also suitable for the specific VFD being used. The VFD documentation should provide information on the recommended fuse type and ampacity rating. If the 3.210 LPJ SB fuse does not meet the VFD requirements, an alternative fuse with a higher ampacity rating or different characteristics may be necessary. Always consult the VFD manufacturer's recommendations and relevant electrical codes and standards to ensure proper overcurrent protection. Ultimately, the correct sizing of feeders and selection of overcurrent protection devices are crucial for the safe and reliable operation of VFD-controlled motor systems. By adhering to the NEC guidelines and considering the specific requirements of the VFD and motors involved, potential problems can be avoided and the longevity of the equipment can be ensured. Considering the intricacies of applying the National Electrical Code, or NEC, particularly Article 430 concerning motor circuits and controllers to systems incorporating variable frequency drives, or VFDs, necessitates careful deliberation regarding feeder sizing and overcurrent protection. The primary principle revolves around the VFD role as the power conversion equipment, distinct from the motor controls. This distinction dictates that feeder sizing should predominantly consider the VFD rated input power rather than merely the motor's full load amps, or flow. This approach ensures adequate capacity to accommodate the VFD current draw during operation. The VFD converts incoming AC power into the specific voltage and frequency required by the motor, enabling variable speed control. This conversion process inherently draws current from the feeder, with the magnitude of current often exceeding the motor's FLA, especially during acceleration or low-speed operation. Consequently, neglecting to account for the VFD input power during feeder sizing can lead to an undersized feeder, resulting in potential issues such as overheating, voltage drops, and premature equipment failure. In accordance with the NEC, feeder sizing for multiple motors or a combination of motors and other loads mandates factoring in 125% of the full load current rating of the largest motor, along with the sum of the full load current ratings of all other motors in the group. However, in the context of VFD-controlled systems, this translates to utilizing 125% of the rated input current of the largest VFD, supplemented by the sum of the rated input currents of all other VFD. This calculation ensures that the feeder possesses sufficient capacity to handle the cumulative current demand of all VFD operating concurrently, while also incorporating a safety margin for unforeseen circumstances. Regarding overcurrent protection, it is imperative to safeguard both the motor and the VFD from excessive current that could lead to damage or failure. While resources such as the Busman SPD motor circuit protection tables offer valuable guidance on selecting appropriate fuses for motor circuits, it is crucial to ascertain that the selected fuse also provides adequate protection for the VFD itself. Specific VFD manufacturers may recommend particular types of fuses, such as faster-acting fuses, designed to protect the VFD-sensitive electronic components from transient overcurrents. The chosen fuse should possess an ampacity rating that is sufficient to accommodate the normal operating current of both the VFD and the motor, while also being capable of tripping rapidly enough to mitigate damage in the event of a fault or overload condition. In the given example, the recommendation of a 3.210 LPG SB fuse for a 1 horsepower motor should be carefully evaluated in the context of the specific VFD being employed. It is essential to consult the VFD documentation or manufacturer's recommendations to determine the appropriate fuse type and ampacity rating. If the 3.210 LPG SB fuse does not align with the VFD protection requirements, an alternative fuse with a higher ampacity rating or different operating characteristics may be necessary to ensure optimal protection. Adhering to the VFD manufacturer's recommendations, consulting relevant electrical codes and standards, and exercising sound engineering judgment are all paramount in ensuring proper overcurrent protection for VFD-controlled motor systems. In summary, the proper sizing of feeders and selection of overcurrent protection devices are indispensable for the safe, reliable, and efficient operation of VFD-controlled motor systems. By adhering to the guidelines outlined in NEC, considering the specific requirements of the VFD and motors involved, and consulting manufacturers' recommendations, potential problems can be averted, and the longevity and performance of the equipment can be maximized. The correct application of NEC Article 430 in relation to variable frequency drives or VFD is crucial for ensuring the safety and reliability of electrical systems. The focus should primarily be on the rated input power of the VFD, not merely the motor's full load amps or flaw when sizing feeders. This is because the VFD acts as the power conversion equipment, and its current draw can significantly exceed the motor's FLA, particularly during acceleration or at lower speeds. Overlooking the VFD input power can lead to undersized feeders, causing overheating, voltage drops, and potential equipment failure. When sizing feeders for multiple motors controlled by VFD, the NEC requires considering 125% of the rated input current of the largest VFD, plus the sum of the rated input currents of all other VFD. This calculation ensures adequate capacity to handle the combined current demand of all VFD with a built-in safety margin. For overcurrent protection, both the motor and the VFD must be protected from excessive current. While resources like the Bussmann SPD motor circuit protection tables offer guidance for motor circuits, it's essential to verify that the selected fuse also provides sufficient protection for the VFD. VFD manufacturers may recommend specific fuse types, such as faster-acting fuses, to protect the VFD-sensitive electronic components. The chosen fuse should have an ampacity rating that accommodates the normal operating current of both the VFD and motor, while tripping quickly enough to prevent damage during faults or overloads. If a 3.210 LPJSB fuse is recommended for a 1 horsepower motor, it's important to confirm its suitability for the specific VFD being used, consulting the VFD documentation for the recommended fuse type and ampacity rating. If the fuse is inadequate, an alternative fuse with appropriate characteristics is necessary. Proper feeder sizing and overcurrent protection are essential for the safe and reliable operation of VFD-controlled motor systems, achieved by adhering to NEC guidelines, considering VFD and motor requirements, and consulting manufacturer recommendations.